Hi, this is Victor Morganti from Fact Engine. Today we're going to be looking at computed columns in databases and derived fact types in object role modeling. Now, to get to computed columns, I'm going to first introduce you to derived fact types in object role modeling. And derived fact types are something that are quite often made out to be something far more difficult than what they really are. And so let's make it as easy as possible to understand, and the beauty of having it in video format is that you can watch this video as many times as you like. We're sitting in front of the Boston conceptual modeling software, and we've got a model open in front of us. It's the Northwind database from Microsoft, and the Northwind database is a database that looks at orders made by customers for one or more products that are supplied by a supplier, and that the order has a shipper and the customer has a demographic, and orders were taken by employees that cover regions in territories now, or territories in regions. We're going to focus today on orders for products and where there's a many-to-many relationship between order and product. So a customer can make an order for one or more products, and a product of course can have more than one order. So we've got a many-to-many relationship between order and product. Now, we know in Boston we can morph to our corresponding entity relationship diagram, and we're looking at the same schema but as an entity relationship diagram, where a customer made an order that has order details, and the order was for a product, and the many-to-many relationship in the entity relationship diagram intimates the relationship between order, or enforces the relationship between order and product, where an order can have many products or be for many products, and a product can have many orders. For each order detail, we've got the unit price that was charged for the product, the quantity that was purchased, and any discount that was applied to that particular line item for our order. Now, we know in the Northwind database that this discount amount is a percentage discount, so to calculate the line item total price, you'd say unit price times the quantity times 1 minus the discount amount to get the percentage of the unit price times quantity to get our line item total. Now, if we wanted the total amount for the whole order, we'd have to add up the total amount for each line item. Now, you can see here we've got a field or a record on our order table that says order total. Now, this particular column or field is not in the Northwind database. It's a calculated column in our model inside Boston. If I go to the ORM verbalization view, which points to the underlying object role model for the schema, and click on order total, we can see that order total is an attribute. It's got its data type, so it's numeric float double precision, and it's derived. So, and it's calculated as order has order total is where order is for product. So order is for product, and we're returning the order ID and the calculated price for each line item. So order detail unit price times order detail quantity times 1 minus order detail discount, and we're getting the sum of those for all line items to calculate the order total for our order. So it's a fairly simple calculation. It's a fairly simple query, and in Fact Engine and Boston this is done pretty much in natural language, and derived fact types in Fact Engine are based on fact type query language, which is a controlled natural language query language. So we're saying order has order total is where order is for product. Now when we say order is for product, we know we're talking about order detail, and we're returning the order ID and the sum of the calculation of the line item total, and we're returning that as order total. We get a clearer view of that when we actually look at the actual object role model. So this is the underlying object role model, which is used to generate the entity relationship diagram and the property graph schema inside Boston, and where we're saying customer placed an order with this fact type, customer placed order, and where order has product or order is for product, and that's this fact type, which is objectified. And as an objectified fact type, order detail has an association with quantity, unit price and discount. So our order detail is an objectified fact type that has an association with quantity, unit price and discount for each line item for that order. Now, if we want the order total, and we do that as a derived fact type, I can look up order total here in the model dictionary, and hopefully I'll find that derived fact type, and here it is. So I'll just put it like that for now, and I'll save the model. So we're saying order has order total, and this asterisk says that it's a derived fact type, and as a derived fact type it has a derivation rule, or the derivation text, and where that is our rule. So order has order total is where order is for product, so where order is for product. And if I click on that fact type and have a look at its readings, one of its reading is order is for product, so that's a valid fact type reading. So order is for product, and we're returning order ID and the calculated line item price and the sum of those to get our order total. And we're calculating the line item price by quantity times unit price times 1 minus the discount against order detail. And fact engine query language and derivation rules in object role modeling and in Boston is fact engine is smart enough to know that when we say order is for product, we're talking about order detail. So I'll go over that again slowly. So our order can have multiple products, and each line item, so each order detail, has a quantity, unit price and discount. If we want the total price for our order, or the total cost of our order, we need to calculate for each and every order detail the quantity times unit price times 1 minus the discount. So we say order has order total, order has order total. This asterisk says that it's a derived fact type, and we're saying is where order is for product, and we're returning order ID, and the calculation for the sum of all total price for our line items. Order detail unit price times order detail quantity times 1 minus order detail discount. We get the sum of that, and that's our order total. So we know then that if we go to fact engine, we can write a query order, and we can nominate a specific order, say 10760, and we can say has which order total, and hit go on that, and the order total for that order is $2,917. Now let's say we wanted to know the total amount that's ever been ordered for a particular customer in our Northwind database for our business. In a similar fashion, we can have a derived fact type which totals all of these order totals for that customer. Now I've already created a derived fact type for that. I should be able to find it easy enough in the model dictionary if I do a search on total, and here it is. So I'll just make that a bit easier to read. I'll just save the model first, and we're saying customer has total customer value, and where total has total customer value is where customer placed an order that has order total, and we're returning the customer ID and the sum of all order totals. So where a customer placed an order that has an order total, and we're getting the sum of all the order totals, and that's the total value of our customer over their lifetime with our business as it's stored in our Northwind database. So it's a derived fact type. If I go to the entity relationship diagram, it's against our entity customer, and here's its derivation in the verbalization, but we know it's not actually stored in the database. It's a derived fact type, and it's a computed column against our table in our schema. Now some databases support computed columns and will support actually storing rules like this against the column, against the table in the database. And you really have to look at each database on an individual basis to understand if they support that feature and how they support that feature in the database. So Boston and Fact Engine support it as a feature that can be used from within Boston or from within Fact Engine, or if you use Fact Engine as an API, a web-based API, or as a type of middleware, you can call a query which will return the order total or the total customer value. Now let's go back to Fact Engine and have a look at a particular customer. So we're going to say customer, and we'll just get the first customer, so Wolski, and we're going to say that customer, so Wolski Zajazd, which is an interesting name, has which total customer value. So what's the total of all the order totals for the customer? So what's the total amount they've ever ordered from us in our Northwind business and as stored in our database. Let's hit go on that. And the total value is $3,531.95. So the customer Wolski or Volsky Jazard has spent a total of, or ordered at least a total of $3,531.95 with our Northwind business and as stored in our database. Now we can look at the query behind that, but first of all let's have a look at the original query for order total. So if we once again say order and we say 1076 or 760, sorry, as which order total, and we can have a look at the SQL in this case query behind that. We've got a subquery which implements our derived fact type. So where we said that we're returning the order ID and the sum of unit price times quantity times 1 minus order details discount, and then we're returning that as order total. As a subquery, it's joined to orders. Notice that in Fact Engine, because we've specified orders 10760, in our subquery we speed things up by referencing that particular order ID. We join that to an order 10760. So it's a fairly straightforward query where we've got a virtual table basically joined to orders, and we're returning the order total. So I'll hit go on that, and we've got $2,917 is the total for that particular order. Now when we say customer Volsky Zajard, as which total customer value, and hit go on that. Again, we have $3,531.95. Our query this time has not only our subquery for order total, but it's also got a subquery for our derived fact type for the customer as total customer value. And we join that to customers up the top here, and we get our results. So we hit go on that, I'll hit go up here, $3,531.95. Now some might say, well geez, that looks like a bit of an expensive query or difficult to write. Well, the query itself wasn't difficult to write. All we had to write was customer Volsky Gerard has which total customer value, and Fact Engine automatically writes our query for us, so we don't have to worry about that. Creating the derived fact type is very straightforward. We can do that in quasi-natural language, so in controlled natural language, and we just defined our derived fact types for order total or our total customer value. And let's not forget that in a database, a lot of this can be done directly inside the database as a computed column. So you can actually store this type of query directly in your column, against your column in your database. And where really there's a lot easier way to do things if you're going to do this sort of query on a regular basis, and you're at least concerned about the time it takes to return the query. I mean, we saw, that's pretty blindingly fast to return that. But let's have a look at how you might do that more simply. Some might say, geez, you need a special database to do that sort of thing, or you've got to use some sort of deterministic logic system or something like that inside your database to handle that sort of thing elegantly. Let's have a look at how elegant even a computer can do this sort of thing. This is ChatGPT, and I'm just going to paste a set of details here. Down the bottom here, I've just got the basis for our query. So our 4 tables: customer, orders, order details, and product. I've nominated the fields that we'll be using in our query, and then I've simply said to ChatGPT, write me an SQL to get the customer's total lifetime value, where the total for an order is the sum of quantity times unit price times 1 minus discount. And we're going to see something quite interesting here. So GPT goes away and thinks about that, and it comes back with a very simple and elegant solution. So this query, I'll just let it finish there. If I take that query, and hopefully I can run that directly inside Fact Engine. So I'm going to dispense of this set of derived fact types, and I'm just going to run this query, and I'm going to look for Volsky. He's down the bottom here, so Volsky Gerard, and here's our total value, $3,531.95, with a very simple query. And you can scratch your head and wonder how ChatGPT pulled that off. Well, there's no mystery to it at all. If we look at our order details again, we've got 3 ostensible object types, or 3 object types, and where customer placed an order that has order detail, and we're basing our total ultimately on these 3 columns within order detail. But really we only have to do a join across these 3 object types. So in our entity relationship diagram, customer, order and order detail, if we go back to Fact Engine and look at our query, if we just do a join across customer, orders and order detail, and we do a group by, but we sum all of the quantity times unit price times 1 minus discount as the total lifetime value, hit go on that, look for Volsky, Jazard again, and there's our value, our total. So even though when we did it using derived fact types we ended up with a complex query, of course there's a much easier way to do it, and I would suggest look around. Don't be tricked into throwing out your database to buy another one just because we haven't thought of the easiest solution. If you need to use derived fact types, the option is there. If you need a blindingly fast solution, of course the simpler solution is there. If on the other hand you're absolutely stuck and you need in your middleware the ability to have that derived fact type up and going in no time at all, you can employ the Fact Engine API and set up your derived fact type for that particular computed column on your table, and get the job done quickly and easily and efficiently. Then as you progress and you need a more rock solid solution, you can work with your database administrator to get that derived fact type put in as a computed column within your database itself. Now some databases will do something very clever. They'll only recalculate something like order total if it's related fields are updated. So if unit price, quantity or discount are updated, then order total will be updated. But otherwise order total will be calculated and stored against the table as any other column, and the cost on doing the query is no greater than any other query against that table. So it pays to get to know your database, it pays to look for a database that is going to service your needs, and if you need to, then finding a solution that offers the equivalent of derived fact types and computed columns can make your life very easy. So thanks for watching. That's derived fact types in object role modeling and computed columns in databases.